Yes, good evening, students. Welcome Sunday. I hope you all are enjoying weekends. Some students requested me to make a video on the counter and memory interfacing. So before I start the video, let me talk that we already made some videos on basic concepts. We also made some videos on combination sequential circuits along with practical implications. So you can check out those videos also. And some students mentioned that some queries are also asked or some come to their mind, so I would be more than happy to answer their queries. So we can have a live session, and you can write in the comment box whenever the most of the students or most of the audience are interested to take a live session. So I would be more than happy to answer your queries in a live session, so that your concepts can be more clear, and your doubts can be removed. Okay, so this is Dr. Kamalkant Sharma, your mentor, your guide, your teacher, and more than a teacher, I'm your friend. I just want to clear your doubts about any kind of topic, right? And this is, I think, fifth video I'm making on this digital electronics. So this is counters and memory interfacing. I will break this topic into two videos. We will discuss about counters, and in the later video, in another video, we will talk about memory interfacing and the registers also. So welcome students again. Without wasting time, I'm going to start. So, but when we say counters, today's topic of the lecture of the video is counters and memory interfacing. So when I say counters, I guess what the exact thing come in your mind, that any element, any device which count, right? So, but in digital electronics, we can count, but as I already told, you can check on my previous video of combination sequential circuit, in which we discussed that we require a clock, because it can be synchronized, it can be asynchronized, it can be mixture of both. It can be considered a feedback, because memory is considered as a feedback in a sequential circuit along with combinational circuits. So when we talk about counters, we have various classification. Again, there are various definition available in different books. Like if I talk about counters, you don't have to worry about it. You have to understand what counter is all about. So counter, first of all, you have to remember it's not a combinational circuit, because when you're going to count, you are going to discuss or going to consider the past and the present values of the input. And when you talk about past values of the input, you're talking about nothing but your sequential circuit, a memory, which can be temporary, which can be your permanent. Okay. So first of all, you have to understand that what is that. If we talk about counter and flip flop, in counter we're talking about sequence of state. Okay, and over here we are very much emphasize on clock pulse. When I say clock pulse, I already discussed in sequential circuit video that we are having different types of clocks, or three different type of triggering methods. One is event driven, one is pulse driven, and one is clock driven. Over here we are talking about clock. Okay, and in that particular video I also discussed about the pulse and clock. Okay, I gave an example of ECG. If you remember, in ECG we are having a PQRS. Okay, and in this PQRS we can see that they are pulses. We say it's pulse, we don't say it's clock. Okay, so input pulses, yes, they are called count pulses, and maybe clock pulses or originate from external source or internal source, and they need to be periodic in nature. I hope you know periodic, that they have to be occur after regular intervals of time, right? So these sequence of states may follow some binary count, or they can be used in different devices, integration of devices also. So first counter we talk about, that is binary counter. So you can see that we have two states, 0 0, and the next state can be also 0 1. Similarly, if your state is 1, the next state would be 1 1 0. If it is 1 0, the next state would be 1 1, and if it is 1 1, then it would be 0 0. So I hope you understand, this is a clock pulse, or the clock defined. Whenever the clock is there, it would be shifted from 0 to 1 or 1 to 0. So it is working like a switch. So when we talk about binary counter, it follow the binary sequence, and n bit binary counter, n bit. I'm again repeating, n bit binary counter, where we have a counter, we will have n number of flip flops. So if I'm dealing with 4-bit binary counter, if I'm dealing with 4-bit binary counter, I will have 4 flip flops that can vary from 0 to 2n minus 1. Now this is very, very important. See students, if I'm making a 4-bit binary counter, I'm going to count from 0 to 7, right? So when I talk about 0 to 7, that means I am counting 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So we are dealing with binary value, but binary counter has some limitations. That is, an n bit binary counter will consist of only n number of flip flops with counting from 0 to n minus 1, where n is the same number which we are dealing with. Now have an example of this binary counter. Here we are talking about the sum truth table. Okay, and the inputs we are also shifting over here. You can see that the 0 is shifting to 0 and the next state would be 1. Similarly, in that case, the input is 1. So you can see this, consider this input as a clock. If the clock is there, then then your next state would be also accumulated or shifted. Now you can see over here, you are having a present and the state Q1 and Q0 as 0, 1. The input is 0, you can say clock is 0. So we are having 1, 0. But wherever the clock is there, it will shift it. 0, 1, the clock is 1, it will be shifted to 0, 0. So that is very, very important. You have to understand this binary counter concept. The binary counter consisting of flip-flop, as I already told you, the flip-flop carries 1 bit of information. I hope this is clear. So basically, broadly, we talk about the counters and we talk about two principal categories in which we talk about asynchronous counter and synchronous counter. Students might, you see my previous video in which I talk about asynchronous counters are event driven. Asynchronous counters are event driven, and the other name of asynchronous counters is ripple counters. Now you can see that in asynchronous counters, the clock won't be same for every flip-flop. And if you are having number of flip-flops, just try to understand. I'm just giving you an overview. I'm not going into detail in the whiteboard or other classroom techniques. But yes, you can write in a comment box if some query is not, if you have any query or something is not clear from the video. When we talk about asynchronous ripple counters, the same clock pulse is not given and the first flip-flop is clocked by an external clock pulse and it is going on. That means each successive flip-flop will be clocked by the output of the first flip-flop or the previous flip-flop. Assume I'm having two flip-flop and I'm dealing with asynchronous counters. So the output of first flip-flop would act, would act as a clock for second flip-flop and so on. Whereas in synchronous counter, same clock would be given to every flip-flop, irrespective of the number of the flip-flops. We also categorize the counters on the basis of application. Now you can see we are having a ring counter, Johnson counter, decade counter, and up and down counter. You will see yourself these counters have very great significance, great impact. But remember students, these counters, what you are reading over here, what you are understanding over here in the video, they are just the basic counters and you have to understand the basic how the counter work. Now, as I already told you that when we have a asynchronous counter, the flip-flop transition serves and triggering is done by the previous flip-flop, whereas the clock pulse would be given to only one single flip-flop. On the other hand, in the synchronous counter, the clock would be given to all flip-flops. Okay, and the change of the state would depend upon the flip-flop output. I am again repeating, the change of the state depend upon the previous flip-flop, and triggering, it can be up triggering, rise triggering, or fall triggering. Let's see. I'm using what kind of flip-flop I'm using. You can write in the comment section. I'm using a toggle flip-flop, and if you remember, I discussed in my previous video about the conversion of flip-flops, where we talk about how the T flip-flop can be made from D flip-flop or SR or JK. And anybody can ask you the question, which flip-flop is not looking for any kind of clock pulse? The answer is SR. Okay, it's a latch. And we already discussed the difference between latch and flip-flop. So this is your asynchronous counter. As you can see, the output of this is nothing but controlling the input of other flip-flop. And as you can see the waveform, you're providing a clock, the Q and Q bar is shown over there. They are both inverted to each other. But you can see the clock pulse, okay, which is twice. Now you can see that edge triggering. Now what I try to say about edge triggering, in a layman language, it is rising and automatically it would go with the rising again. So the twice of as long. The output will be clock whose period is twice as long. I hope I make it very clear. So when I talk about 2-bit asynchronous counter, that was a single bit. Now if I talk about 2-bit asynchronous counter, best schematic diagram I try to show in a video so that it would be simple and it should be clear to you. The basic concept should be clear to you. You can see we are having two flip-flops. Naturally, they are JK flip-flop, and the J and K value would be very, very high. And we are widening race or race round condition over here. We are giving a clock. Now you will see that's an asynchronous counter. So the output would be Q, and that Q would operate as a clock. I hope this is clear. So in asynchronous counter, why it is known as 2-bit asynchronous counter? Because we are using two flip-flop. Okay. Similarly, you can see when you're talking about Q0 and Q1, the present state of the next state. Sorry. You can see it is starting from 0 is there because it will remain the same state, and then the 1 is there. Similarly, when the Q1 is the next state, it would start from the next rising, next falling edge. I hope this is clear. Now it can be rising triggered or it can be falling triggered. That totally depend upon the type of flip-flop, type of user interface, and the kind of counter you're going to use. As you can see, it is triggered by negative edge of the Q output of the first one. Right? Now again, 2-bit asynchronous counter. So I already discussed, if you remember, students, we discussed about the propagation delay. When I'm talking about propagation delay, it is the difference between input and output. Okay, so you can see the propagation delay should be very minimum, that is desired. But in D flip-flop, we are having a good amount of propagation delay. So you can see that in an asynchronous counter, all the flip-flops cannot be triggered simultaneously. That's why they are producing an asynchronous operation. Otherwise, if they are triggered simultaneously, they would operate in a synchronous way and they would be named as synchronous counter. So what is the algorithm? All the clear inputs are connected together. I would share one video of experiment implementation of this counter using 7-segment display. So you will see that in this, whenever we are going to use IC, all the clear inputs are connected together. Okay, so that one single pulse can clear all the flip-flop. 2-bit triple counters, we require 2 flip-flop. But how many states we have? 2 end state. That is very, very important. Okay, so 2 end state because we are having a Q and Q bar. And number of states in a counter is known as modulus. So normally we name it mod counter. So remember, asynchronous counters are normally named as your mode counter. Like if I talk about 2-bit counter, it is a mode 4 counter because the states are 4. So modulus value, please remember this, most of these questions are being asked in interview and the IES in the Indian Engineering Services and various engineering platform in the placement interviews. They are modulus. They're not interested that you have to draw a modulus counter, but they are interested whether you know what is modulus. Okay, so modulus is basically dependent upon the number of states of an flip-flop. So we can say a 2-bit counter is nothing but mode 4 counter, right? So you can see the most significant flip-flop produces 1 pulse for every n pulses and significant clock pulse, right? So when we talk about 3-bit asynchronous counter, as you can see, I'm using 3-bit asynchronous counter. That means I am using 3 flip-flop. I hope this is clear. Sorry. So if I'm using 3-bit asynchronous counter, that means I am using 3 flip-flop that is fixed. And the first flip-flop operate, right? The first flip-flop operate, but how it will operate? It will operate depending on the clock output of the first flip-flop would operate at the clock of the second flip-flop and so on. As you can see in a particular timing diagram, the X naught, where the X naught, the flip-flop is connected, over there we are providing a clock pulse, right? And simultaneously, that clock pulse would be shifted to another flip-flop through an output of the flip-flop. So we are having X0, X1, X2, where the clock pulse is being provided. And X0 would be a first one, then it would be second one, then we shifted another one. That's how the counting would be carried out. I hope you're clear with the asynchronous counters. Now we are talking about a ring counter, and you can see a different configuration is there. When I talk about ring counter, you can see in ring counter, we are using a same clock pulse. So the ring counter is named as your synchronous counter. But the other difference, as you can see in ring counter, the feedback is connected. Okay. So this kind of operation is basically meant for SISO. You will see, we will discuss in register when we are going to discuss registers. You will see we are having different shift registers and SISO operation is being carried out. But the main thing in ring counter is that in this counter, the normal output of the last flip-flop is connected to the input of the first one and the feedback is being provided. Whereas in Johnson counter, you can see this kind of operation is basically your serial in parallel out. You will see in the shift register. When I'm saying serial, that means I'm saying the output of first becoming the input of second, output of second becoming the input of third, and so on. This is serial data. All the clear pulses would be connected together so that single pulse can clear all the previous values. And the feedback loop is given. You can see that parallel data output. Okay. So Johnson counter is also known as twisted ring counter. Now, when I say twisted ring counter, it is exactly the ring counter. Only there is one difference between ring and Johnson counter, that inverted output. You can see the feedback. If I go back, you can see in this, not twisted output is given, not the inverted output is given. The same, I already told you, there are two types of feedback. One is positive feedback, one is negative feedback. And when the output is the same proportion, same character is there with respect to input, we name it the positive feedback, otherwise negative feedback. You can see over here the inverted output is getting feedback or giving back to the flip-flop or the input of the flip-flop. This is your Johnson counter. So if anybody asks you what is the difference, you can easily tell that there is a difference between ring and Johnson counter. So let's discuss now how can we design a counter. I hope everybody is clear. What is the operation? What is asynchronous? What is synchronous? What is feedback? How can we differentiate between different types of counters? Now let's talk about designing of this. So when we talk about counters, now we understand that counters are going to store some kind of information, and they're normally used different types of flip-flop. But one condition is there: the flip-flop should be same. You can use n number of flip-flop, but the flip-flop has to be same. The only requirement, why we do that, why we consider this, why we put this limitation. Assume you are using JK and T flip-flop. In JK flip-flop, we are having two inputs. In T flip-flop, we are having one input. That would be very difficult to manage the operation of different types of flip-flop. Right? So we normally don't prefer, don't recommend. Okay, so n-bit counter having two end states that we already discussed, and two end states as basically modulus. And modulus, if I say modulus n counter, it's the two end states and varying from 0 to 2n minus 1. Again, I'm using the word cascading. Deliberately, I'm using the using the word cascading, because cascading, you know very well, the output will become exactly the input. Otherwise, in coupling, no, it's not the case. Okay, so that's why due to this mod, because you are dividing the input clock frequency by the mod, and that's why we name it a frequency divider. If I ask you how many this is the exercise I'm leaving to you. How many flip-flops are required for mode 8 counter, mode 10 counter? You can tell. Okay, and you can reply in a comment section also. So when I talk about classification of counter, I'll discuss that on the basic of asynchronous and asynchronous. In asynchronous, the clock pulse won't be same. In asynchronous, the output of one becomes the second, input of second. In synchronous, it is not the case. Every flip flop would be given in front of you, as you can see in the synchronous way. You are getting an operation, so it is basically a serial output. Yes, and the clock pulse is given. Now you can see that we summarize the differences between the difference between synchronous and asynchronous counter. So you can see that in synchronous counter, with the increased number of state, we are having it is complicated because the clock pulse has to be same. If I talk about the connection, yes, there is no connection, and yes, it is okay, but propagation delay would be very less in the case of synchronous counter, where in the case of asynchronous counter it is more, and frequency operation is high. And one condition that need to be followed, that all the flip flop has to be clocked at the same time, which is not in the case of asynchronous counter. But normally, out of 100%, 99% of the counter follow the asynchronous operation. If I talk about synchronous counter, you can see that up counter, down counter, and a random sequence. What is the algorithm? What is the status? What is the steps we can follow? First of all, we have to calculate how many number of flip flops we are going to use for a counter. Then draw the state diagram. You can draw the appropriate flip flop. Minima, you can use K-map also, and then the circuit diagram logics. Now, one example I'm taking care of, you can see over here, a 3-bit asynchronous counter. No, the difference between a 3-bit asynchronous, 3-bit synchronous counter. Sorry. So 3-bit synchronous binary counter, I'm using T flip flop. Normally in making counter, we use T flip flop and D flip flop instead of JK and SR. So you can see that what I write over here, I write the present state. If you see over here, it is writing from 0 to 7. The next state is starting from 0 to 7 and going back to 0. And in this case, you can see that we are going towards that how that T flip flop would operate. Okay, so this is very important, and the flip flop T2, T1, and T0, because the clock pulse would be high, T0 would be remain high every time. T1 depend upon the present in the next state, so automatically it is going to change, and similar T2. So you can see that T2 is Q1 into Q0, T1 is equal to Q0, T0 is equal to 1. That is your K-map, already discussed in the basic concepts video. But just remember, in this case, we are having a 3 variables, and 3 variables we are dealing with triangular K-map. We're not dealing with rectangular K-map. Okay. For this, you can check my previous video of the basic concepts. So when we talk about binary 4-bit synchronous up counters, now when it is synchronous 4-bit, so we are going to use 4 flip-flop, that is fixed. Synchronous, that means we are going to use clock pulse. Okay, and we are providing it over here, and different combination or the delay we can provide. So one thing is very much clear, that the separate AND gates, we normally use AND gates for transfer information. This is a 4-bit synchronous counter waveform user timing diagram. So I already discussed with you in detail. If you remember, the QA would start from it is 0, it is starting from 1. The next QB it is 0 0 and starting from 1 again. So that is how we are going to count. Decade 4-bit synchronous counter. When we talk about decade 4-bit synchronous counter, so basically when we talk about decade, we are talking about we're going to count from 0 to 9. Okay, and we are going to count from 0 to 9. It's a decimal number. Decade counter decimal value is 10, you know very well. So after reaching the count of 1001, it backs to 0. So you can see we are going to 0 to 9 and 0. Okay, so it's a synchronous counter. The clock pulse would be given, and we are going to AND gate. This circuit diagram you can derive from the K-map also. Now we have a 4-bit up-down counter. You can see over here. When I'm talking about up-down counter, it would be more interesting, students, when you will move to shift registers. When you will see registers, how the registers would operate depending on this operation, the counters. Now, when it is 4-bit up-down counter, we are using 4 flip-flop. Okay, and the output is be taken out, but it isn't taken out in the parallel mode. Okay, so no feedback is there as such. The last counter that is very, very important. After this, we will only revise the other counters. We are having bidirectional counter. Very, very important counter nowadays. Bidirectional counter, as the name suggests, that these are basically, this can be synchronous also, this can be asynchronous also. And the other name of bidirectional counter is basically universal counter, which can be used for counting up and down. Okay. And when we are going to use bidirectional counter, when there's up and down counter, they're going to count in, and they're capable of counting in particular direction, depending upon the sequence, and they can be reversed also. This is the beauty of a bidirectional counter having a different sequence. This we already discussed in counter, but I am again repeating because earlier in the video you saw the ring counter circuit diagram, but now we are going to discuss is working also, the ring counter, what is the working of ring counter, how it is going to operate. First of all, it's just a revision of the ring counter for you. Ring counter is a cascaded operation. The flip-flop, we normally use D flip-flop. As I already told you, in the counter, they're going to use D or T flip-flop. So common clock signal, all the inputs are going to set and clear. We have to decide the number of states. Number of states would be dependent upon number of flip-flop. Then 4-bit counter using 4 flip-flop, and number of states would be 4. You can see that over a logic diagram ring counter. It is a 4-bit. Okay, and the condition is 00001, 0000000, 0001, 0010, and 00110. And feedback is already been given. So you can see the truth table of ring counter. Whenever don't need to cram it again. The clock is 0, all the output are 0. When the clock is 1, Q0 is on, all are off. Clock is again 1 after a pulse, after a delay. Then Q1 is on, all are off. Then clock is again 1, so Q2 is on. The clock is again 1 after delay, the Q3 is on. What is the difference? When the clock is 1, due to this feedback, the Q0 will turn on. Right? This is the beauty of your ring counter. I hope this is clear to everybody. This is a waveform of ring counter, and I hope you are clear about it. The waveform ring counter clear would be given to everyone. Clock similarly, it is 00 and then it is 001. See, after 2 clock pulses, after 2 pulses, it is getting started. It is a falling, it is a rising edge. Now you can trigger by the falling edge, but then you have to maintain a pattern. Counter is nothing but a sequence. It can be random sequence also, but it should be follow certain kind of sequence which can be made out. Okay. So like we can see the Johnson counter, again it's a revision of Johnson counter. So another name is twisted ring counters, also known as mode 2 and counters. Okay, number of stage depend on the twice the number of flip-flop used. That is very, very important. Okay, so half the number of flip-flop we are going to use. Basically, the only requirement, only objective is to reduce the number of flip-flop. If it is a 4-bit counter, we have to use 4 flip-flops, as you can see already in the previous slides. But in Johnson counter, our objective is to reduce the number of flip-flops. So you can see the output is connected to the flip-flop that we already discussed. Is the theoretical part. So let's go to truth table and the circuit diagram. Now you can see that in the Johnson counter, you can see the 4 flip-flops are there. We are giving a 1 clear signal and the inversion is given. Let's see the truth table now. Here no clock is there, so all the outputs are 0. When the clock is there, the same process is started. But when the clock pulse is again given, two clock Q and QB are on. I hope this is clear, because we are talking about QA, QB, QC, QD in a separate day. I am going back to ring counter. You can check out. In Johnson counter, what is the two step we follow? First QA, QB, then it would be QA, QB, QC, and then it would be QA, QB, QC, QD, and then it start QB coming back. I hope this is clear. So it is going in reverse order and a forward order both. So this is how the Johnson counter we talk about. There's a timing diagram of Johnson counter. Okay, this timing diagram is very, very important. CSC students, those are going to read microprocessor or microcontroller in their coming semesters, or if they already have some knowledge about microprocessor, microcontroller, this timing diagram is very, very important to understand. I made it clear in the previous video also, and this video also. So any query you can write in the comment section. Certain application we use for ring counter or Johnson counter, up down counters. Normally I segregate the application in the terms of ring and Johnson counter only. Ring counters are basically used as a frequency prescaler. They also use as crypto analysis. Nowadays we're talking about cryptography, right? They are accumulator counter. We are having a accumulator register in 8085 or in a microprocessor. Over here, I just want to mention there is a difference between microprocessor and microcontroller. Controller is for specific purpose and processor is for general purpose. Similarly, for Johnson counter, it indicates the motion in 2 dimension. It can go with SAIC or FPGA design. You can search out what is FPGA. But if you want to know from my side, it is field process gate array. So frequency of the clock by varying the feedback, and we can use different phase shifting for the ring and Johnson counter. So I am logging off from the counters, but yes, I just summarize what we discussed in this video. We discuss how the counters are made. We discuss the basic definition of counter, why counter is required, what is the classification of counter on the basis of the application and their configuration, what is timing diagram, how the counter works, what are the different counters we have in terms of asynchronous, synchronous, and we also discuss the application of counter, right? So in of extension to this, I will discuss registers and memory in the next video. Okay, so that you can club that, yes, whatever you learned in a counter, that can be easily applied in your practicals. Even though if you want to make any kind of project, you can easily think of that, yes, how this concept of counter can be implicated, can be used in making some memory interface unit. This is all from my side. Dr. Kamalkant Sharma logging off. Thank you. Thank you again.